Welcome everybody in a new video. In the last video we have seen the theory behind the Thevenin theorem. In this video we'll try to do an exercise with a bit more complicated circuit, just to try this theorem more and to understand it better, okay? So we have this circuit, as you can see, is a bit more complicated than the previous one. We have two voltage sources. The first one, it has 50 volt. The second voltage source, it has 100 volt. Then we have a current source. It has 0.2 ampere. And we have 5 resistors. The first one is 100 ohm, the second resistor is 200 ohm, the third is 300 ohm, okay, 400, 500, okay. Let's imagine our objective, our final goal is to find the current who flows here, who flows to resistor 5. We want to find this current. This is our objective, okay. This is our final goal, okay. We have to find this current. So how can we do? We'll use the Thevenin theorem, but using it just once will not be enough here. We can use it more than one time, okay? In this case, we'll use it 1 and 2 times, okay? I can also find this current in other ways using Kirchhoff principles, okay? There are other ways, but we'll use Thevenin theorem 1 time and 2 times, okay? And 2 times, okay? So let's begin. Let's begin to simplify this circuit using Thevenin theorem. So the first thing I want to do here is I will cut off these circuits here in this 2.1 and 2. So I'll cut off these 2 wires. Remember, you can cut off just 2 wires, okay? No more, not less. 2 wires, okay? So we'll cut off 1 and 2. The circuit in these 2 points, A and B, okay. So we have cut off the circuit here, and let's take this part and just put it aside. We are interested now in this other part. So let's pick this part of the circuits, let's copy it back here, let's copy it here, and let's transform it with Thevenin theorem, okay. So let's take this part. This part is formed by a voltage source, 2 resistors, and another voltage source, okay. So we take this part of the circuit. And we know we have to transform all this part of the circuits, we have to transform it in just 2 components, a Thevenin voltage source and a Thevenin resistor, okay. So how can we do? Well, for the Thevenin voltage source, we have to find actually the voltage drop between the point A and the point B. We have to find the voltage drop here. Imagine you take a voltmeter, okay, an instrument to measure the voltage, and you put it here, okay. The value of volt you got here is exactly what we are searching for, okay. So to find the voltage drop here, the value of voltage here, we have to consider this circuit as a... So we have to analyze this circuit. What is this circuit? Well, we can consider it as a closed loop circuit, just this. Okay, our circuit is just this, because these 2 wires, they bring to nothing, okay? So current will not flow here, they are just connected to nothing, they're just, okay? You just open it here, okay? So if current does not flow here and does not flow here, this is just a closed loop circuit, okay? It's just made like this. So we'll have a current flowing this way or this other way, we don't know. Let's find out what will happen here. Well, I have a first voltage source here, and it has 50 volt. This other one is 100 volts, so this one is superior to this, okay? So we can use Kirchhoff principle. We can easily understand that current will flow in this direction, okay? So current will flow in this direction. But let's use Kirchhoff principles to understand how much is the current, how much is the value of this current, okay? So if we write a Kirchhoff equation here, let's write it. what we have to do is to decide a direction of current. We can decide clockwise or counterclockwise. It's the same. You can decide the direction you prefer. Okay. Then you do all your calculation. Okay. Then you do your calculus. You calculate how much is the current, how much are the voltages. Okay. If you have a negative result, let's imagine we have a negative result of the current, a negative value of the current. Well, it doesn't mean that you are wrong. The value is correct. Okay, the current it has that value, it is correct. But if you have a negative result, it just means that it goes in the other direction. Okay, so you are correct, but not in the direction. The direction was the other one. But you can decide direction clockwise or counterclockwise. Okay, and what is important is to keep coherence with that direction you have chosen, okay, in all the equation. Okay, so let's decide counterclockwise because it seems more appropriate in this case. So let's decide counterclockwise. If the direction of current is this, well, what will happen in this circuit? I will have a voltage drop here on this resistor VR2 and another voltage drop here on this other resistor. The voltage drops on the resistors, well, they have the opposite direction of current. If current flows this way, the voltage drops are in the opposite way. Okay, current this way and voltage drop this way. Here, current goes this way and voltage drops this way. Okay, so I will have this. Now let's write the equation of this circuit. Let's begin from here. Everything that goes in the same direction of current is positive, and everything that goes in the opposite direction of current is negative. Okay, so A2, this voltage is in the same direction of current, so it's positive. Okay. Then we encounter this, and this is in the opposite direction of current, so A2 minus VR2. Then we encounter this voltage drop, and it is in the opposite direction of current, so it is negative. Then we encounter this, and this is positioned in the opposite direction of current, so this one is negative too. Okay, and all of this is equal to 0 because the algebraic sum of all the voltages in a mesh, in a closed loop circuit, is always equal to 0. So this is our Kirchhoff equation for this circuit. Okay. Now let's write what we know here. Okay, let's substitute. Let's do just this. Let's write what we know. Okay, A2 we know how much is it? It is 100 volt. VR2, how much is it? Well, VR2 is the current who flows in this circuit multiplied for R2 minus VR1. What is VR1? Well, VR1 is the current who flows through this circuit multiplied for R1 minus A1. A1 is 50 volt. Okay, and all of this is equal to 0. So now we know the value of R2 and R1, so I can write the value of R2 and R1, okay, in place of just writing R1 and R2. Okay, let's write them. So the equation is 100 volt minus I multiplied for R2, which is 200, okay, minus the current multiplied for R1, which is 100, minus 50 volt, okay, which is A1. Okay, so this is our equation. Now it is one equation, one unknown term, so we can easily solve it. Okay, this one and this one, they are both negative, okay, and they both contain I, so I can just sum them together. Okay, so the equation here will be 100 minus 200, 100, okay, 300, okay, minus 50 volt. Okay, so this is our equation. Now this one is positive and this one is negative, so I just do 100 minus 50, okay, and the result is 50. So what remains is 50 minus 300. I equals 0. Okay, this is our equation now. So now this will go here. Okay. Now we have this. Now I divide both of them for 300. Okay, I do this. What happens here is that 300 divided for 300, they just go away. What remains is this. 50 divided for 300 is equal to our current I. Okay, let's just do this and we'll find the value of this current. Okay, 0.16. Okay, this is our current. Now we know the current who flows here. We know the value of this current, and this is the correct direction. Current flows in this direction. But now we have to understand how much is the voltage drop here and how much is it. Well, we just have to understand that here we don't have just a resistor. Well, here we have also a voltage source. Okay, so we have to understand what does it happens here. The first thing we have to do is to calculate the voltage drop exactly on resistor 2. The voltage drop on resistor 2 is the current multiplied for R2, okay? Is this, and we know the value of the current now, which is 0.166 ampere. This is the value of the current, and R2 is 200. So let's just do this and let's find out how much is the voltage drop on R2. The value is 33.2 volt. Okay, this is the voltage drop on R2, and the direction of the voltage drop is this. Okay, because we have a current flowing in this direction, so the direction of the voltage drop is this. Okay, so here in this exact place we have, let's just consider this place, okay? We have a voltage drop in this direction and another voltage here in this other direction. Okay, it is positioned in this other direction. So if we measure the voltage here in this place, we have to do this minus this, okay, because they are in opposite directions. So I have to find the equivalent. Okay, I cannot just put them together because they are opposite, so it is one minus the other one, the bigger one minus the smaller one. I have to do this. Okay, so A2 minus VR2 is equal to, let's find out, 100 minus 33.2. well, the result is 66.8 volt. Okay, so this is the result. So this, what is this? This is the result of this algebraic sum of these two voltages. Okay, this is our VAB. This is the voltage we have if we take an instrument to measure the voltage, and we put this instrument here. What we will find is exactly this value. So a voltage with this value, and let's keep an eye on the direction. It is important to remember the direction. The direction is this. The direction of the voltage is this. Why it is important to remember the direction? Because the direction of this VAB is the direction of the Thevenin voltage source. Okay, if the direction would have been the opposite one, the Thevenin voltage source would have been upside down. Okay, so remember the direction. Not just, you don't just have to calculate the value, you have to keep in mind to remember the direction, okay, to understand the direction. So this is our voltage, Thevenin voltage generator, Thevenin voltage source is this. The VAB is the Thevenin voltage source. we have find it. Now let's concentrate on the Thevenin equivalent resistors. Okay, how can I find this? Well, I have to copy these circuits again, but this time in place of voltage source I have to put just a wire, basically. I say I put them in short circuit. I have just to put a wire in place of the voltage source. Okay, so what I do is this. Resistor 1 and resistor 2. We have just put a wire in place of the voltage source. Okay, now I can calculate the equivalent resistor, the total resistor, but by the point of view of these 2 points. I have to imagine, we are just imagining here that I have like a voltage source here. Okay, if I have a voltage source here, how much would it will be the total resistance here? Well, it will just be R1 in parallel with R2, R1 parallel R2. This will be just the total resistance. Okay, so the resistance between the point A and B is just R1 parallel R2. Okay, I just have to do this. So I have to do R1 multiplied for R2 divided for R1 plus R2. I just have to do this. Okay, let's do this. So okay, let's do this. I use my calculator here and okay, the result is 66.7. Okay, this is our total resistance from the point of view of this point, of the point A and B. From this point of view, the total resistance is this. Okay, so this is the RAB. It means that this is the Thevenin resistance. Okay, this one. So now we have the Thevenin voltage source and we also have the Thevenin resistance. Okay, so we can transform all this part of circuit in just 2 components, the Thevenin voltage source and the Thevenin resistance. Let's do it. So the Thevenin voltage source, we'll put it in this direction, as you can see. Okay, because the direction was this, so we'll respect this direction. Okay, as you can see, the positive is here and the negative here. Also we have our Thevenin resistance, and here we have the point A and the point B. So now we'll just now that the circuit is transformed, it has been transformed, we'll just place it back where it was. We have cut off this part of the circuit. Okay, we have take this part of the circuit, we have transformed it, and now that it is transformed, we'll just place it back here. Okay, we'll just place it back here. So let's copy all this other part. Okay, we have this. Here we have a resistor, if I am not wrong. I don't. Okay, a resistor and another resistor. Okay, so now we have this. It is a bit less complicated, but still it is not a circuit I can easily, let's say I can easily solve this circuit. It is not a circuit I can easily solve. Okay. Now I could find this current in many other ways. Okay, no, but we want to do it using Thevenin theorem. So what can I do? I have to cut the circuit again. Okay, where I could cut it here? No, I will not do this. I will cut it here. I will cut it here, okay? In these 2 points, I cut these 2 whites, and let's call them C and D, okay? A, B, C, and D, okay? Why I haven't cut it here? I will explain you just in a moment. Let's imagine we have cut it here, but okay, but let's imagine I have cut it here. We would have find in a very not really good situation. Let's imagine I cut the circuit here. We would have find in this situation where I have the voltage source, then the Thevenin resistors. Here we have the current source, and here the other resistor, okay? So if I cut the circuit in this way, I could not find the voltage here exactly, because if I do this, I have to imagine this circuit as a closed loop, but I can't because I have a current generator here. And if I have a current generator here, well, it will be a bit more complicated, because the branches with a current generator, with a current source, nothing can enter inside here. Nothing can enter inside here. So I have to consider this as a closed circuit, okay? So what happens here is that the circuit will be kinda like this, okay? It will be like this. But here I have a current who it will be something like this. You understand, it is still possible to calculate something, but it is a situation a bit so I prefer to avoid this situation, okay? Because we have this, and where does this current goes? It apparently nowhere. So it is a bit it is a situation that is better to avoid this, okay? So let's not do this. Let's do this, okay? Let's cut the circuit here, let's copy all this part, and let's transform it, okay? And then we'll place it back here. So let's take this part of the circuit, okay? All of this, and let's copy it back here. So we have this, then this. I could draw it more bigger. Yes, I'll draw it a bit more. Okay, we have this. What else we got? Another resistor here. Okay, so this is what we got. So what we have to find now? Well, now we have to find a second Thevenin voltage source, but we'll call it VTH2 because it is the second time we are doing this, and a Thevenin equivalent resistor, we'll call it RTH2 because it is the second time we are applying the Thevenin theorem, okay? So this is the circuit we have. How can we consider this circuit? Well, we have to use Kirchhoff principles here to understand what happens here. Okay, so we have to write the Kirchhoff equation of this circuit. First, we have to decide the direction of the current, clockwise or counterclockwise. I'll pick clockwise this time, okay? Here, this branch, it has a current source, so I cannot consider this as a real branch. I have to consider this as it does not exist, almost does not exist. The only things that this branch does, the only thing that this wire does is there is a current here who flows in the circuit, who enter in the circuit from here, okay? But nothing else can enter in this branch. So this branch is kinda like it does not exist, okay? So we have just one closed loop circuit here. it is like we have one closed loop circuit, and it is this one you see here. Okay, so we decide the direction of the current, which is clockwise this time, and we'll write the Kirchhoff equation considering this mesh, this closed loop circuit. Okay, now let's write it. If current flows in this direction, how will be positioned the voltage drops? Well, I will have a voltage drop here. I will have a voltage drop here in this direction, because the voltage drops on the resistors are always in the opposite direction of the current. Okay, so I will have a voltage drop here, and I will have another voltage drop here. Okay, so let's write the Kirchhoff equation of this mesh, of this closed loop circuit. The Kirchhoff equation is VTH minus VRTH and minus VR4. All of this is equal to 0, because the algebraic sum of all the voltages in a mesh, in a closed loop circuit, it is always equal to 0, okay? But this time I also have to write another thing. I also have to write the equation of nodes. How many nodes are in this circuit? Well, just 1 and 2, okay? This other one, I can not consider them as a nodes, because these wires brings to nothing. So this wire and this wire, it is like they do not exist, okay? So I have one node here. Let's call it M. What happens in this node? Well, I have this I0 who goes inside. I also have this I who goes inside, this current here who goes inside. Let's call it I1, okay? And I have this other current who flows outside, okay? These two go inside, and this one go outside, flows outside. Let's call it A4, okay? So let's write the equation of this node. The equation of this node is I1 plus I0 is equal to I4. This is the equation of the nodes. Now let's substitute all the terms we know, all the things we know. Let's write all the things we know, and let's just keep as unknown just the thing we don't know. Okay. Sorry, sometimes I speak a bit weird. I know English is not my real language, so try to understand. I apologize. Okay, let's keep writing this equation. Okay. VTH we already know it. We calculated it here, and it is 66.8 volts. VRTH, well, it is I1 multiplied for RTH. Let's write this for the moment. And VR4, what is it? It is the current who flows through R4, this current multiplied for R4. So it is I4 multiplied for R4. Okay, this is exactly this. Okay. Now in this equation we just know this one and this one are unknown. Okay, so let's write I0 is how much is it? 0.2. Okay. Okay, now we can keep improving this equation, writing the value of this and this, because we know this and this. Okay, let's do it. 66.8 volt minus, how much is RTH? The first RTH, it is just where is it? It's here. It's 66.7. Okay, this is RTH. multiplied for I1 minus R4, which is 400, multiplied for I4, and we don't know how much is I4 for now. Well, all of this is equal to 0, and the second equation is I1 plus 0.2 is equal to I4. Okay, this is our Kirchhoff equation now. Two equations, two unknown terms, so we can find them. Okay. Now we know that I4 is equal to I1 plus 0.2, so let's change I4 with this. Okay, let's change I4 with this, because I4 is equal to this, so we can change I4 with this. Okay, we can do this. Let's exchange, okay, I4 with this. In place of I4, we'll write this. Okay, let's not write the second equation, we don't need to write it again. Let's concentrate on this for now. Now we have one equation and one unknown term, so we can find it. We can find the value of I1 now. (400) multiplied for I1, the result is 400 I1. And then 400 multiplied for 0.2, the result is, let's find out, 80. So minus 80 equal to 0. Okay. So this is our equation now. This one and this one, they are both negative and they both contain, they both have I1 as a unknown term, so I can just put them together. I can just add them together, put negative, so I just put them together, and the result is 466.7 I1. Sorry, minus 80 equal to 0. Okay, I have this equation now. I have this equation. I just have to do this minus 80. The result is minus 30.2. Okay, volt, but okay. Okay, so this is what we got now. Now I will take this and I will put it on this other side. Okay, now I will divide both of these for this value. And here again. So in this case, what happens is just they just simplify each other. So okay, but here I have to do this division. So now we have this. Now we have to do this. Let's find out how much is the value. The value is minus 0.028. Okay. So as you can see, the value is negative here. What does it mean? Well, the value is correct, but what does it mean? It's just that I was wrong about the direction. The direction of current is not this, but the direction of current is in this other way, is this. Okay, so the direction of current is this. In this closed loop circuit, the current flows in this direction, okay? The current, especially here, what I need is this. Now we have to find how much is this current, okay? But here the I1, it flows in this direction. Okay, so I1 does not flow in this direction, but in this other direction. Now we have to find I4. Okay, we know that I1 is this. Let's find out I4. And let's place let's exchange this with I1 here, because I1 has this value. Okay, I will do it here. Okay, so I1 is minus 0.028. Okay, plus 0.2 is equal to I4. Okay, so this is what is the value of I4. Let's find out how much is it. Okay, the result is still positive, so I was entirely wrong. Okay, so in this case we have this I4 with a positive result. So it means that yes, about I1 the direction was wrong. I1 flows in this way, but I4 no, I4 flows in this way. Okay, so the direction of I4 is this. Okay, is exactly this. So we have like a current here who flows in this way, then a current here who flows in this way, and another current here who flows in this way. Okay, these are the correct direction. Anyway, now we have I4. This is what we need. We have this current, so we can find the voltage drop on this resistor. This is what we are searching for. So since we have I4, VR4 is just I4 multiplied for R4. It's just this. The value of I4 is 400 ohms, so we just have to make 0.171. 400, and the result is 68.4. Okay, 68.4 volt. This is the voltage drop on R4. Okay, and it has this direction. Remember always the direction, because if the current here flows in this direction, okay, it means that the voltage drop will be in this direction. Okay, so we have found VR4, and this means we have found VCD, and this means we have found this. Okay, we have found VTH2, which is exactly 68 point. Okay, so we have VTH2. We got it, this direction. Now we have to find the RTH2. So let's copy all this circuit, and this time we have to do this. We will put just a wire in place of the voltage source. We will short circuit the voltage source, and also this time we have a current source, and in place of current source we don't put a wire in place of current source. We don't put them in short circuit. No, for the current source it is different. When there are current source, we just let the circuit open it. In this way, I'll show you. We do this. Okay, here there is the RTH. We have R4 here, and here we have our points C and D. Here we have R3, here there was the Thevenin voltage source, and here there was the current source. Okay, in place of the current source we put this. We just let the circuit open it. Okay, this is what we do. So now if we have this situation, okay, if we have this situation here, now we have just let the circuit open it, how can I calculate the total resistance seen by the point of view of these 2 points? Well, if I use an instrument to measure the total resistance and I put it in these 2 points, what I see from these 2 points is just this and this, because this is an open circuit, so it doesn't count. It is like this does not exist. Okay, so the total resistance seen by these 2 points, it is just this parallel this. Okay, it is just RTH parallel R4. This is the RCD, the total resistance seen by these 2 points, and this means that this is also RTH2. This is what we are searching. Okay, so let's just do this. RTH multiplied for R4 divided for RTH plus R4. We just have to do this. Okay, we just have to do this. How much is RTH? RTH is, I don't remember, how much is it? Okay, it's 66.7. Okay, multiplied for okay, this is our resistance. Okay, multiplied for R4, which is 400. And here, down here, we have 66.7 plus 400. Okay, so we have to do this. Let's calculate it. Okay, the result is 57. Almost, see, almost this, 57 ohm, and this is our RTH2. Okay, so now we have found RTH2 and VTH2. So now I can transform all this circuit, I can transform all of this in just 2 components. VTH2, a voltage source, a Thevenin voltage source, and a Thevenin equivalent total resistance, okay? A Thevenin resistance. So let's transform all of this in just these 2 components. So we have VTH2, which is positioned in this direction, okay, because it was upward, okay? This is VTH2, and we have RTH. Now we have our points C and D. And now that this circuit is transformed, we'll just place it back where it was before. We will just, okay, we have transformed this part of the circuit, all this part, it is now transformed. So now we'll just place it back here, okay? If we just place it back here, we obtain this. Okay, so now we have this. This is a very, very simple circuit. If we want to calculate the current here, it will be very easy. We just have to do VTH2 divided for RTH2 plus R5. We just have to do this. So let's calculate this, and we'll find this current is called I5, but it is just a current who flows through the whole circuit, okay? So let's calculate this. VTH2 is, how much is it? 60 8.4 volt. RTH2 is 57 ohm and R5 is 500 ohm. So we just have to do this and we'll find our current. Okay. Okay, the result is 0.12. This is now our I5 and this was our final goal, our primary goal. Okay, it was to find, our primary objective was to find this current. Okay, and we have found it. We have found it using Thevenin theorem, but we have used it 2 times. Okay, 0.12. This is the current we have found using Thevenin theorem 2 times in a bit more complicated circuit. Okay, I hope you have understood everything I have done in this video. I hope this has been helpful to you to understand better how Thevenin theorem works. And well, if you have any question, feel free to ask in the comments. I'll do everything possible to answer you.